then you'll start things off, Sophie. Yeah?
Yeah, we are live now. But we'll just wait a couple of minutes before we get started.
Hi, good morning, everybody. I think we'll get started. A couple of more people are coming in, but I'd like to thank you all for joining us. A special thank you to Craig Wadham this morning for the original lead on this. Big thank you to Sam Fleischman from Duolingo for all of his support in bringing this together, and a very warm welcome to Geoff Flair. Geoff will be presenting the session today. Geoff has a PhD in applied linguistics. He specializes in language assessment, corpus linguistics, and quantitative research methods. He has research published in Language Testing, Applied Linguistics, the Modern Language Journal, and Transactions of the Association for Computational Linguistics. So Geoff is currently the Senior Assessment Scientist at Duolingo, and his primary responsibilities include research and development of the Duolingo test. So thank you for speaking to us today, Geoff, and we're looking forward to hearing from you.
Thank you, Kara, and thank you for having me. I am excited to be here. And so the title of my talk today is, I'm guessing everyone can see this, or Kara, can you see this and give me a thumbs up? Okay. The title of my talk is Digital First Approaches to the Development of English Language Assessments. What I have in store for today is an overview of the mission and motivation of the Duolingo English test, and then I'm going to dive into its structure and how we use automatic item generation in the development of the test. And then I'm going to give you a peek into how we ensure domain representativeness and estimate the difficulty of our vocabulary items, and do something similar with our passages, right? Show how we classify our passages into different domains and estimate their difficulty. And then I'll move into discussion. And so my goal really is to talk about the role of technology in the development of assessments and use the Duolingo English test as an example, because I think we are one test where, technology does play a primary or a large role in the development, administration, and evaluation of the assessment. And it does all really start with the mission of Duolingo and the Duolingo English test, where for Duolingo, it's to develop the best education in the world and make it universally available. And then for Duolingo English test is to use technology to lower barriers to assessment and increase opportunities for English language learners everywhere. And I'm not just, up here just relaying the mission, because the mission really is something that underpins why the test was created. And so what's interesting is around the same time the Duolingo English test was created, Anthony Kunin was publishing some articles about, why you might create a new test and fairness in assessment. And so he argues that the motivation to build an assessment is to resolve some difficulties and bring about some benefits to society. And my argument here is not that, that Duolingo was reading this text when they decided to create this assessment, but while this paper was coming out, Duolingo was being contacted by users of their app, and they were asking them for opportunities to certify their English language proficiency. And so Duolingo took a look at the landscape and saw it, said, what is out there, and what kind of difficulties could we potentially resolve with our skill set? And one was location, right? So test centers, they can be difficult to reach if you're not in a highly populated area. Sometimes it can cost a lot of money and take a lot of time to get there to a test center. Additionally, like taking the test can take a lot of time, and sometimes it takes a lot of time for score turnaround. And finally, affordability. Tests can be expensive. And so for Duolingo, they asked themselves, how can technology be leveraged to resolve these difficulties? And the first solution was to administer the test via the internet. And this is a map that shows, number of internet connections per million people across the world. So you can see that a lot of countries have a lot of internet connections. Central Africa is still even underserved by this model of administering the test via the internet, and so are some places in Asia, but largely access to the internet is pretty prevalent across the world. The second solution was to create a computer adaptive test. So this is a test that after a short burn-in phase, which is what you see here in this illustration, the first 4 items, each test taker gets an item that increases in difficulty, and after the 4th item, a provisional estimate of ability is made, and then that provisional estimate updates with every item that the test taker sees, and also importantly, the selection of the subsequent item is selected to challenge the test taker, right? So we can get the most information about their ability at the delivery of each item. Additionally, we use automated scoring. We automatically score the speaking and writing, and then we keep a very, very short turnaround time. And we're able to do that because of the automated scoring of the items. And so we deliver score reports in less than 48 hours is our service level agreement. And then finally, getting to cost, the way we try and keep that down is by leveraging machine learning and NLP processes to create our items, and then also to estimate their difficulty so that they can be administered in a CAT format. So one of the important resources in administering a CAT is having a large item pool of calibrated items so that you can make accurate decisions about which item comes next. And this last bit is really the focus of what I'm going to be talking about today in the rest of the presentation. I think it is important, however, to understand the structure of the test if you're not familiar with it. So largely, we have 7 item types on the test. We've got our performance-based item, which I have these at the top of the table because we're not going to be talking about them, but we're talking about the other ones at the bottom. So these ones actually happen at the end of the test. We have a speaking section and a writing section. Within those 2 sections, their test takers are asked to describe pictures and then respond to your traditional independent prompts, where they might be asked to make an argument or narrate a story or recount a story. Then moving on, we have what we call text vocab and audio vocab items. And so these are yes/no vocabulary tests where test takers are asked to discriminate between real English words and pseudo-English words. So these are, measures of vocabulary size, which are predictive of test takers' reading and writing and listening and speaking abilities, respectively. We include dictation items and elicited speech items, and then we include C-test items as well. And I'm going to run through what these look like on the test. So this is what our independent writing task looks like. We ask test takers to respond to the question in at least 50 words. There is no limit in the box. They can, respond to as much as they want in the 5 minutes that they have. Similar with the, independent speaking task. I think I understand a lot of you work in language assessment, so you're probably familiar with these formats. With the independent speaking, one of the independent prompts is delivered orally, right? So it's an audio prompt. And then we have the speaking picture description and the writing picture description. And so these constitute our open-ended tasks. This is what our yes/no vocabulary tasks look like. We have the text variant on the left, and you can see, some non-English words, some other nainate, and then we've got the audio vocab on the right where you can't see the words, but when test takers click on the buttons that say sound, it plays the word. It speaks the word to them. And then our dictation and elicited speech. Again, I think these are what you would expect. You hear a statement and then they have to type it, and then they read, for the elicited speech, they read the statement aloud. And finally, our C-test passages. These follow the traditional C-test format in terms of how we damage the words. The first sentence is left completely intact. The last sentence is left completely intact. And in the intermediary sentences, every other word is damaged with the exception of proper nouns and numbers. And so across these item types, we have over 20,000 items in the bank. Most are drawn or sampled from extant open corpora. For the CAT portion, there are 5 to 8 of these on each test after the end of after the end of an administration. And we use what we call human in the loop automatic item generation. AIG is automatic item generation processes to estimate the difficulty. And so each one of these has a unique ML difficulty estimate that we use in the administration. And so this is an image that gives a high-level overview of how the automatic item generation process works. Okay, so I'll walk through the top level first. So we start with the Cepher annotated or Cepher informed and expert annotated text and word lists. So we gather words and passages, and we literally make lists in like data frames, in like Excel files or in Google Sheets. We ensure domain representation from, I'm going to dive deeper into this, but a quick overview is that we use like COCA, the Corpus of Contemporary American English, for sampling vocabulary words. And then we have an internal corpus that we use to match passages to domains of study in university. We run them through what we call FAB review, fairness and bias review. And then because some of these are, is language found in the wild, sometimes that does have to be edited. So it goes through edits, some minor edits. And then we ask experts to label the words and passages. So we have two separate models. One is the vocabulary model, the other is the passage model. And when we first developed these, our experts, people with graduate degrees in applied linguistics or TESOL and teaching experience, they labeled a large number of passages along 6 buckets that are representative of the CEFR, and for both the passages and the words. And then we take that data, we take those labels and the passages, and we run them through the statistical models or the machine learning models or the NLP models, if you will, so that they understand what the features of the words are at each difficulty level. And then for the passage model, what the features of the passages are at each difficulty model or at each difficulty level. And then what this allows us to do is create a large calibrated item bank for a cat, because once we learn the models, then we can do this process that I have illustrated on the bottom, which is get a lot more natural English language sources, run them through those same statistical models that learn the features of the words and the passages at each level, and it then projects them onto the same difficulty scale as the ones that we used for training. And so what this does is what we called in a paper that we published in Tackle and the Transactions for the Association of Computational Linguistics, it helps solve what we call the cold start problem. And so this is, the problem is obtaining item difficulty estimates prior to operational administration. So traditionally this is done through very extensive pilot testing, getting a large number of observations per items after items have been written, and then seeing which items are performing as expected, and then screening out the bad ones and keeping the good ones. And so what we're doing here is learning the difficulty of the items based on some language or linguistic characteristics and projecting them onto that difficulty scale. And so we have these passages that are identified as being more or less difficult by our experts. And that's how we started to solve this cold start problem. And now we're going to sort of dive into the nitty gritty for the vocabulary model and then the word model, or the vocabulary model and then the passage model. And so like one of the first questions you could ask of this is, okay, what is done in the design stages to ensure representation of different domains of English, such as academic and general English, and how are the item difficulties estimated? And so the way we do this is how I say through some corpus linguistics and 3 machine learning models. So with the corpus linguistics research and processes that we use rely on looking at frequency and dispersion of words across word lists, and then for passages, making register-based comparisons. And in the development, like I mentioned, we have our word model, our passage model. I neglected to mention earlier our domain classifier, which is also an important step in this process. So for vocabulary, we start with the corpus of contemporary American English. And this is a screenshot of the current composition of the corpus. It has a number of genres: spoken, fiction, magazine, academic, weblog, and TV and movies. And importantly, within these genres, it has like subgenres or subregisters. And so within academic, you can see that it has texts from social sciences, history, humanities, medicine, science, and technology. And so we use this corpus to identify vocabulary that could be described as academic vocabulary or general vocabulary. And I'm going to talk about 2 indices that we use to help make that decision, like automatically, right? And one is frequency based. So for academic vocabulary, a word must occur at least 50 times in the academic corpus. And for general vocabulary, it must occur at least 100 times for it to be a candidate to be included in the yes/no vocabulary tasks. And then also importantly, we look at an index called dispersion. And this is a measure of how evenly a word is spread out across the disciplines within each of these domains. So how evenly is a word that occurs 100 times spread out across all of the subdisciplines in the academic corpus. And so what this does is it helps us control for vocabulary that might be too domain specific. So a word could occur 100 times, but it might occur 100 times within a single subdiscipline. And that might make it not just an academic vocabulary word, but really a word that is only relevant to, say, law or to, say, science and technology. So we're looking for words that are evenly distributed across the academic corpus, and similarly for the general vocabulary corpus. And I got a little bit ahead of myself there from my review on my slides. So this does ensure that we're sampling words that occur typically across all target domains, not just within one, right? And so this way we have good representation of words that could be, that you could argue are general language vocabulary words or academic vocabulary words. And these indices and these processes come from other researchers, right? Gardner and Davies' development of the academic vocabulary list, and then a paper that has come out recently by Egbert and Biber and Birch, 2020, and this was a paper about dispersion. And so then we take that then we have these words. Once we have these words that are academic or general, we just have a long list of words. And the next step is to say, okay, how difficult are these words? Which words should be on the most difficult items and which words should be on the easiest items? And so again, we return to this ML process. I find it nice to remind people of these steps. So we start with our annotated word lists, right? And so we ask people to label these words, and then we run them through our statistical models. And so the model from Settles et al. 2020 is one that looks at character length. Okay, so the length of characters. So if we had flirpy as, say, a non-word, that is 6 characters long. And then we look at the likelihood of the sequence of the characters within that word. And so that's the second line, the log likelihood of sequence. And then we look at the Fisher score, which is sort of like the individual likelihood of these unigrams, bigrams, and trigrams. And what's nice about this is this here is not necessarily something that is of interest from an applied linguistics perspective, but it does work on all words. It works on both real words and it works on both pseudo words. So we can get estimates of the difficulty of the pseudo words as well. And then also importantly, we evaluate this, especially for the real words. So in this plot here, you see our vocabulary model prediction on the y-axis and our Cepher expert judgments on the x-axis. And this is actually a correlation coefficient of like 0.92. And so we see a strong relationship, a strong agreement between our expert judgments of difficulty as well as the vocabulary model prediction of a item's difficulty. And what we end up with are these items that you see on the right, which look sort of maybe basic or easy to interact with, but there is a lot of interesting work that goes into the development of them. It ensures that we use a corpus that represents different target domains of interest to ensure that we are including words that represent these target domains on the items. We've got these automated indices that can project the difficulty of these words onto our scale that we learned from labels that people gave to them. And then we can use that information to create our groups of items. So when we create our groups of items, it's not like we don't have a word like desk next to a word like, I don't know, anti-disestablishmentarianism, which I don't think would be on the test anyways, but we have words at similar levels on each of these, what you might call cards, right, within each one of these items to make the task of discriminating between real words and pseudo words a little bit more difficult. Okay. Moving into the passages. So there are sort of 3 processes that we've used for the passages. One is the domain classifier, the other is difficulty estimation, and the other is a linguistic evaluation of what's going on in the passages. So for domain classification, we wanted to know, how well are we representing these different target language use domains across the entire set of our thousands and thousands of C-test items. What we did was we used a tool called BERT, so bidirectional encoder representations from transformers, BERT, BERT. This is a large language model that has come out in the past few years. And it can be used to extract what we call vector representations that capture syntactic and semantic attributes of the passages. And I'm going to dive in quick a little bit to say what this means. So when you run a passage through BERT, you get a vector representation, which is basically a large data frame of 768 indices that are not directly interpretable, but it does represent interesting things about the passage. So if you were to give it a passage and it had a phrase that said something like John was at the bank of the river versus John robbed the bank, it would encode bank in those two contexts differently, because BERT can look before the word and after the word to understand the context that the word is in. So while maybe the 768 indices can't be described, it is understanding these nuances in how you can use the word bank, or the different meanings of the word bank. And in order to learn what a domain looked like, we built an in-house textbook corpus that represents 5 domains: math and computer science, business, social science, engineering, and then the life and physical sciences. So it totals 170 books, almost 60 million words. And then we can run the books from those domains through BERT, and then BERT learns and understands what the language within a math and computer science book looks like, what the language within business textbooks look like, and what the language within life and physical sciences books look like. And then we can use this and we can run our C-test passages through the learned statistical model, and it can identify where these passages belong in this subset of domains. And then finally, because like I mentioned, BERT's output is not really interpretable, we wanted to better understand what was going on in these C-test passages. So we compare the lexicogrammatical characteristics of the C-test passages to text from other target domains. The method we use is called multidimensional analysis. It originated in the sociolinguistics literature it comes out of Doug Biber and Conrad's work, where they compare different registers of language use, right? So office hours, narratives, textbooks. And it has been used in test development. It was used to describe the domain of university language knowledge in the development of TOEFL IBT. And more recently, this method is being used to describe the speaking and writing responses that are elicited by speaking and writing tasks in high stakes language assessment. And at its core, what it does is it reduces a large number of interpretable linguistic features down to a smaller set of functions of language use using exploratory factor analysis. And so I'm going to dig into this a little bit more. What you do is you have these large numbers of linguistic features, and you reduce them down, and you get these factors, and you call them dimensions. And then you look at the features that are loading on the dimensions. And sometimes, like dimension 1 here, you have features that load positively on a dimension, meaning the features that load positively, these things tend to co-occur together. So when you have past tense verbs and third person pronouns, you're also getting all other pronouns, you're getting adverbs, you're often getting contractions and activity verbs. And then you have these negatively loading features, which when these are occurring, right, when you get attributive adjectives, other adjectives and longer words and pre-modifying nouns and present tense, these are often coming along with them, right? Sort of coming along for the ride. And then you look at, which linguistic features are loading on which dimensions, and then you give them names because people use these linguistic features to achieve a function of language use, right? So colloquial narrative is the name we are giving to dimension 1, and then technical exposition to the negative side of dimension 1. And so passages that are that have a preponderance of these linguistic features, right? The negative linguistic features or the positive linguistic features are representative of these dimensions. And interestingly, you can look across different registers, and you can define registers as well by the preponderance or the lack of the preponderance of these linguistic features also. So if you take, for example, this colloquial narrative excerpt, which is pulling from our fiction corpus here, right? We see a lot of past tense, a lot of pronouns. And you can see here, the colloquial fiction has a large, on average, or the median score on this dimension is very positive. And there are some down in the negatives, but the majority of them are positive. And importantly, you can see that our C-test passages here, we've got a point for each of the C-test passages in our item bank. These are overlapping with the fiction passages. And what that tells us is that we do have C-test passages that have similar linguistic features that you would find in colloquial narrative writing. And then news as well, you see how news sort of spreads out across this dimension, both being colloquial narrative and some technical exposition. And the C-test does as well. It spans out across this dimension also, and then overlaps with textbooks, which are heavily more technical exposition. And so here's an example of a technical exposition passage where you've got noun-noun sequences and longer nouns. And so I think the key takeaways from this is that it's possible to use corpus linguistic methods to check on to check on the development of our passages and see how well they are representing different domains from a register-based perspective. And it is possible to use these machine learning models to identify, which domains our passages for our C-tests come from and which ones they represent in our textbook corpus. And finally, with the evaluation, right, we have a strong relationship between our ML difficulty and our human ratings. So it's possible to build these word models, right? These models that are arguably character-based, but can strongly predict the difficulty of a word. And then finally, we've got this corpus-based analysis that shows a good overlap of our lexicogrammatical features. Now we're moving on to one of the things that I think is one of the more interesting. I think all of this is interesting, but I think this is the most interesting part of what we're doing, and it's the difficulty estimation of passages. So again, we return to the ML process. At the beginning, this follows the same steps as the word model. We have a set of passages that we ask experts to label. And then the next step, we've actually done two different things, and I'm going to discuss those two different things, is run them through different statistical models to estimate their difficulty. So in Settles et al., we ran them through statistical models that looked at characters per word, words per sentences, the log likelihood of a word, and its Fisher information score as well, similar to the word model. And we compared different ways of estimating their difficulty using linear regression and weighted softmax regression. But that was 5 or more years ago that we did this. And now we've got these, large language models such as BERT. So we're turning our eyes back towards BERT again, that have been trained on these really, really large corpora. And again, I'm going to say this again because even for me, sometimes it's hard to get my heads wrapped around what we're doing here. This can be used to extract these vector representations. So again, it's a 768 dimension data frame that encodes the syntactic and semantic attributes of the passage, which is not always easily interpretable when you look at these vector representations, because the columns are literally just numbers, and then what's inside of the columns are also just numbers. So it's not like this corpus-based method where you can look at the output and say, yes, that's a noun. Yes, that's a noun-noun sequence. And so in discussing this, the first question that we asked ourselves is, does BERT embeddings plus observed data in what we call linear logistic test model, which is just an extension of a Roche model, if you're familiar with that, does it create accurate estimations of item difficulty? And if so, can we use what it learns, and can it generalize to unseen items? And then finally, a similar question as the one before, do the BERT and LLTM produce difficulty estimates that are related to functional dimensions of language? And so here we have a couple different ways of evaluating how well it's working. One is what we call our Cepher labeled metrics. And this is basically, how well does a model, how well does a machine learning model explain the same labels that a person has given it? And for this, we look at Pearson's R and Spearman's Rho. So these are normal measures of agreement. And then we have what we call our test taker response metrics, which is really how well does the model predict the difficulty compared with the observed difficulty. So we look at the relationship between the expected and observed difficulty. We look at the standard deviation of the residuals. So how spread out are the errors. We look at the item type total correlation. So this is all for the C-test passage. When we create the scores for the test takers on the C-test passages, how strong is that relationship with the total score of the test without those items in it, right? So we create the total score without the C-test passages. And then the test-retest reliability, right? How strong is the test-retest reliability coefficient? And then finally, for the linguistic evaluation, we follow a similar method or the same method. We use multidimensional analysis. So we tagged each C-test passage using the Biber tagger, identified the meaningful linguistic features that we wanted to run through the factor analysis. We run the factor analysis and we explain 45% of linguistic variance, which is a little bit higher than average. And then we functionally interpret the factors like I explained from the last study. And then finally, we look at the relationship between the difficulty estimates and the factors. So we have our 4,000 labeled passages from Settles et al., 700,000 responses to C-test items, and these come from about 100,000 exam sessions, again, with 5 to 8 C-test items per session. And so here's a table of the metrics results. And this is a big table. Our model of interest, like our new model, is the one in the middle there, the BERT LLTM. And then we compared it to 3 baselines. One is all same. This is like saying, okay, if we didn't tell the model anything, how does it perform? The other is the a traditional 2PL IRT. And the third is the original model. And so we see that BERT in bold there, the relationship between BERT's labels of the passages to the Cepher scale is stronger than the Settles et al. Model, and it's not something we could estimate with the 2PL model. And the all same, it was at 0, right? It was just random. And then when we look at the test taker response metrics, we see the 2PL IRT model. It has a slightly higher mean item Pearson's R, and it has a slightly higher standard deviation of the residuals, but the BERT LLTM model's standard error of the residuals is just a little bit higher at I got a little bit confused there. The 2PL's standard deviation of the residuals is slightly smaller, which is what you would want to see at 0.16, but the BERT LLTM model is at 0.17, so not that much different. And then we have a slightly stronger item total correlation and a similar test-retest reliability. Now, where the rubber really hits the road here, so to speak, is with the item split. So this is where we held out items from the model that from the training data. And so the model had never seen these items. And then we run them through to examine how well the model generalizes to unseen items. So how well can it predict the difficulty of items it has never seen before? And so we see that it can do this with very little loss of information, right? The mean item correlation is 0.59, and then the standard deviation of the residuals is 0.17. And so what this means is that we can use the BERT LLTM model to learn about the difficulty of an item, and then use what it learns to project the difficulty of unseen items with a high degree of accuracy. And so what's really interesting about this is how well this actually works with respect to the number of observations you need per item. And so what we see on the left-hand side of this plot is the item type total correlation, right? The Pearson's R relationship, and then number of sessions on a log scale, right? So you've got like 10 and then 1,000. And so what we see is that the BERT LLTM model can create difficulty estimates that correlate, that have an item type correlation of greater than 0.6 with about 500 sessions. For the LLTM model to have that same, to create that same item type total correlation, it takes like 100,000 sessions. And so what's most interesting about this is that 500 sessions does not mean 500 observations per item in a computer adaptive test. With our large item bank, we get very sparse data. This comes down to about 6 to 8 observations per item. So with the BERT features in the LLTM, plus 6 to 8 observations per item, we can make highly accurate predictions of an item's difficulty. So if we move on to the multidimensional analysis, we took a look at the linguistic variation just within the C-test passages. So here we're not comparing it to any other target domains. We're looking at just what's inside the C-test passages. You get 6 dimensions, and I'm going to talk about 2 of them. One is oral involved versus literate informational. And so here you see the oral involved features are positive again, like second person pronouns, contractions, and then literate and informational being just total nouns, longer words, and agentless passives. And then expository versus narrative style. You see, again, the positively loading features are the types of linguistic features you would find in expository writing, such as common nouns, noun-noun sequences, or pre-modifying nouns and abstract nouns, and then a narrative style with past tense verbs and third person pronouns. And so this is what the C-test passages look like within the expository dimension, I guess, continuum. So you see on the left here a sample of an expository C-test passage. You've got your noun-noun sequence. You've got words like equipment and bathrooms, so these common nouns. And then you've got this more narrative style on the right-hand side where you've got past tense verbs and the pronouns, right, and third person pronouns. And what's most interesting about this is the relationship between the dimension scores and the estimates of item difficulty. So in this plot here on the right, item difficulty is on the y-axis on a 0 to 10 scale, and the dimension scores are on the x-axis. And so in this first plot, remember oral and involved language was the positive dimension. So as texts become more positive, you see that they are judged by the model to be easier. And as texts become more negative on this dimension, they are judged to be more difficult by our BERT LLTM model. And this relationship is similar with lexical variability. So as passages become more lexically variable, have a wider range of words, they become more difficult. And as they become more expository was on the positive side of this dimension, they also become more difficult. In fact, of these 6 dimensions, all 6 have good moderate correlations with the exception of epistemic stance. And so I think the takeaways from this one is that we can leverage information about the language in the passage along with response data to create estimates of item difficulty. And these can be made with very small samples. Furthermore, what we learn can be generalized to unseen data with very little loss in accuracy. And so I think what we have here are difficulty estimates that are not just reliant on a population of people, right? So instead of just piloting these items on a very large population of people, we've got a model that takes into account both the people in the response data as well as the features of the language in the passages. From a more applied linguistics perspective, I thought it was interesting that BERT seems to be keying into these features that are functionally interesting or that are related to functional aspects of language use, right? And then furthermore, we can evaluate what BERT is doing by using sort of like rich corpus-based linguistic description. And then from a testing perspective, what it means that, when people take this computer adaptive test, as they are judged by the adaptive algorithm to be more proficient, they are reading more informational, expository, objective texts with higher lexical variability. And as they are judged to be, say, less proficient, they are reading more involved narrative subjective texts with lower lexical variability during the test. And so we started out with like this mission and these difficulties, where, you know, what Duolingo did was identified some difficulties that they thought test takers had in order to access an English language proficiency test, namely location, right? The distance to test centers, how long it takes to travel there and take the test and wait for scores, and then how much a test can cost. And so the solutions that we have leveraged technology in order to resolve these difficulties is, I mean, one is, it sounds like a no-brainer, but it does require a lot of engineering work, is to administer the test via the internet, create a computer adaptive test that can be, you know, administered in a small amount of time. It takes about an hour to take the test, and then leverage these machine learning and NLP processes to generate items in order to keep costs down. And so finally, like when we talk about digital first assessments, I don't think of digital first assessments just as a test that is delivered on a computer, but it's a test that leverages technology in its processes end to end, right? And so we use these, you know, cutting edge, I guess, advances in machine learning, natural language processing, and applied linguistics research in the design stages. And then when we actually create the items as well. And then in the administration, we are using them along with psychometric processes and software engineering, right? Just to get the items to the test takers, even over low bandwidth internet connections. And also to evaluate the quality of the items that we're creating. And then finally, to report scores in a very small window of time. And so what's important about this is that it's, you know, triangulation of these fields. This is sort of like the cornerstone, right? We are trying to take the best that we can from the machine learning fields, the engineering fields, especially with administration, psychometrics, and applied linguistics in order to create this test. And so finally, every time I talk about this test or about what we're doing in the processes, I have to point out this is like, it requires a large team of people to do this. This is not me. I'm not sitting behind a computer doing this. It's a team. And you can see them at that URL there. And that's it.
Thanks very much for that, Geoff. It's really quite interesting to see that what sits behind the test. We've got quite a few questions that are coming through. So if you've got a moment, one of them, thanks Geoff for the technical details of methods used in the Duolingo English test. Of these methods, which of them do you think should be, have been applied in the design of local assessment as distinct from large scale standardized tests?
I think that for local assessment, the development of, I mean, if it's possible, if you have the resources to develop a reference corpus of what's expected of your test takers to read in your universities. So we have one that's based, ours is based on, you know, what's popular across university study, generally writ, or in a general sense, I should say. But that could be highly variable within institutions. And so if I were to be creating a local test, I would think about, you know, reaching out to my colleagues in the different domains and asking them what they are asking their graduates and undergraduates to read. As well as you can think of it from like what they ask them to do as well with language. It doesn't have to be just like reading.
Okay, thank you. Another question. Has a classification analysis been conducted, i.e. to check the rate of classification errors, false positive, false negatives, that DET produces for university admissions purposes? I guess Duolingo is DET.
Yeah. That is an excellent question. And I think the short answer to that is no. This is something that we do have ongoing external research looking at something similar, which is like predictive validity. It's not quite the same as classification errors, but I think it starts to answer a similar question.
Okay. All right, thank you. Couple more. What models did you use to select the question types? For example, select the English word from the pair or complete the word in the closed passage.
Yeah, so, part of this was looking at the literature to see, it was part, what could we do with a cat? So we wanted something that we could administer quickly and then get a lot of information about test taker language proficiency from it. And so that's why we chose these more, integrative tasks from, the OWL perspective. But also, the yes, no vocabulary tasks are, as I described, very easy to create. And so it's a sort of a cheap task to make for us as well. So we get a lot of information for the item without a whole lot of, doesn't take a lot to make these, basically.
I have a follow-up question there about pronunciation. Can you describe the ML utilized to determine accurate pronunciation in spoken answers?
Not in detail, but I can tell how it was developed. So it was trained on non-native English speakers. So when the Duolingo English test first launched, it was free and it was like being piloted. And so we collected all that data and trained our ML speaking model on that data.
Okay. All right. And probably just another question for you, Geoff, around predictive validity, because I suppose a lot of what we're looking at Duolingo use for is students entering, further studies, university studies with using the test as their proficiency entrance. What are your thoughts? Have studies been done on the predictive validity of Duolingo for university studies, or is that likely to be an area of future research?
That is an area of ongoing research right now. We have a group in the UK who are pursuing that, as well as in Canada. The only study to date that's been done is fairly old at this point. It was done on the original version of the test, which was just the computer adaptive version, not the version that has the speaking and writing in it. And it wasn't necessarily a predictive validity. Oh, I guess this actually returns to the classification question. It was actually a classification study. I don't know why I didn't think of this with that question, but they asked ESL faculty members at a smaller university in the United States to classify test takers, and they compared those rates of classification with classification that would be made with the Duolingo English test. And this paper is on this the second URL there, englishtest.duolingo.com/research. I would just, it's just an older, it was done with an older version of the test. So you have to take that with, I guess, a little bit of a grain of salt. Because it's not the exact same test as it was 5 years ago, 6 years ago when they did that study.
Okay. All right. Thank you, Geoff. We've got a member of the, one of the conveners would like to ask a question. Stephen, would you like to pop on to frame your question?
Thanks, Cara. Can you hear me now?
Yes.
Yes.
Okay. Hi, Geoff.
Hello.
Thanks for the presentation. That was great. I've got a question about, I guess, aspects of validity relating to Duolingo. I think that, Duolingo is doing an astounding job in terms of the ease of access, the affordability, the scoring reliability that it provides to test takers. And I think clearly you're pushing a lot of boundaries in the way you're using machine learning, corpus linguistics, automatic item generation in the test development process. But there have been criticisms raised for the use of debt in terms of university admission. And those criticisms relate to things such as the test tasks not having much in common with the types of language tasks that university students engage in, or the context validity. The test not assessing discourse level competence or interactional competence, both seen as key aspects of academic language ability. The potential for negative washback and negative washback into learning in terms of test takers practicing test wiseness strategies and focusing on word lists and things of that nature. So I'm a firm believer in the use of CAT in test design, and I think that CAT can address many of those criticisms that have been raised. Does Duolingo have any plans to change the test design in response to those kinds of criticisms that have been raised?
Yeah, I mean, you bring up good points. And the C-test is not I agree, the C-test is not a task that you would see in an academic language setting, right? It is very much, comes out of this reduced redundancy approach to language testing. I think there's 2 points to make about that. One is that the task might not be as realistic, but we do represent a wide variety of target domains within the language that is in that task. And so we may not be getting, the thing that the people do, but we are asking them to complete this task using academic texts as well as fiction texts or news-like texts. And then the second thing is, to your final question, is we are continually iterating on the test. And so when I joined in 2019, later that summer, that was when we folded in the speaking and writing tasks. And so these are, your traditional independent prompts that you might find on other high stakes tests. And we are always looking forward to the next change. So the short answer to that is yes, we are always exploring opportunities to add to that. Yeah.
Thank you, Geoff.
Thanks for that, Geoff. Probably time for one more question. And I think I have seen on the site, this is a question about conducting concordance studies with Duolingo and other sorts of tests like IELTS and Pearson and TOEFL. I can see that you have done. Has that been done lately? I suppose is more the question. How do the scores compare to those high stake tests?
So that has not been done since 2019, and it is probably worth taking a look at again, given the change in population that we've had over the past year.
Mm-hmm. Okay. All right. Well, I think we're, thank you so much for that, Geoff. I think we'll round things off there. Lots of questions, but lots of long textual sort of questions in there. So perhaps there's a lot of discussion that can continue around this theme. And I think the notion of creating a reference corpus for the creation of our own test is a good way forward, really, for us at the local level. So thank you very much for your session
Welcome.
today.
Thank you.
It's been great. Lots of people interested in this area and lots of really great questions coming through.
Yeah, I agree. Thank you for all the questions. It was great being here. Thanks for having me.
Okay, great. Thank you.
Right.
Thank you, Kara. I appreciate it.
Oh, that's okay. Gosh, can you hear me? Oh my goodness, some of those questions, it was like a page of writing. So I was like, oh my goodness, it was